Edmund, welcome.
Well, good morning. I intend to do the impossible. I intend to explain to you cold fusion. I intend to show you how you can make a sample that works every time. And I'm going to tell you how to commercialize it. I hope that's not too much. In 30 minutes, right. 29:41 right now. The cold fusion requires two approaches. One is based upon how it works, and the other is based upon why it works. I'm going to talk about how it works, but to make that clearer, that distinction clearer, I'd like to give you an analogy. If I'm going to learn how to fly an airplane, I would sit in the airplane and find out what the stick did to its configurations. That's the how. I do not need to know anything about lift or the mechanism of lift. That's the why. We need to focus on the how. The why at this point is too far in the future to have any benefit. So I'm sorry, you theoreticians, you're sort of wasting your time at this point. So let's get into the environment that hydrogen occupies. When I use the word hydrogen, I'm talking about all of the isotopes of hydrogen, deuterium, tritium, anything else that might come along. So hydrogen exists, first of all, in the lattice. In the case of palladium deuteride, it's a face-centered cubic lattice. This is a normal chemical structure. The structure is well known. There's very little ambiguity about it. It's been investigated for almost 100 years. A nuclear reaction simply cannot take place in that structure. I know some of you focus on that structure. You use that in your examples. I think, again, you're wasting your time. It simply cannot happen under those conditions. It would violate too many well-established laws of chemistry and physics. Instead, another environment must be created. I call that the nuclear active environment. That environment is outside of the crystal structure, and it's a place to which the hydrogen can go by a normal chemical process. So it goes from the lattice to the nuclear active environment by a loss of Gibbs energy, just like all chemical reactions occur. Once in this nuclear active environment, it now has the ability to form another structure, which I call the nuclear active structure. That structure is where the action occurs. That's where the actual nuclear reaction occurs. So each nuclear active environment might contain an arbitrary number of NAS. So we have the two variables, the number of nuclear active environment sites and then the number of NAS in those sites that determine what's going to happen. So let's talk about the nature of the nuclear active environment. It has to be something that will attract the hydrogen. In other words, it has to look different than the lattice from which it came. But it has to not allow the formation of the hydrogen molecule. So it has to have what I call it, a range of size. It has to have a critical size. That's what makes it rare and difficult to form. That's why cold fusion is so difficult to reproduce. Getting that environment to form in its correct configuration. Now, I believe that this nuclear active environment are gaps, physical gaps, small cracks, but too small to even see with an electron microscope. So we're talking about something happening on the nanoscale, which is also very frustrating because it's very difficult to study things where you can't see it. I believe the gaps have a couple of nanometers in size, but once they're occupied, they become stable. And the reason for that is their occupation requires the loss of Gibbs energy. Now, for them to revert back to their original condition, that energy has to be resupplied, but it's not available. So fortunately, the condition in which cold fusion happens, once it forms, it's stable, and that's why we can continue to see the process for a significant length of time. The conditions for forming the nuclear reactor environment, I believe, there's a lot of conditions. The ones that I've focused on are the inclusion of inert particles, that is, particles of a material that melt above the melting point of palladium. These, the gaps form between these particles, which are embedded in a random way within the material. And that formation is controllable by the composition. That's where the composition comes in. But the size of the particle also plays a role. The reason why frequently when you have a supply of palladium, it will either be active, and if it is, all of that batch will be active. That's one of the characteristics of this field. And if it's not active, then nothing will happen. So the big issue is why is the material active throughout a batch? It has to be because there's a uniform structure created throughout the material. So, and that can be identified as a distribution of these particles. And these particles result during the fabrication of the material. Palladium frequently is made chemically separated from its impurities. That results in a powder. That powder has to be turned into a solid, and then as a result, melting does that for you. And the melt then allows large particles to float to the surface where they're removed, and but small particles remain behind. So the big question is there any kind of evidence for this? Well, looking at this slide, look at the center, you'll see a cartoon of how I would represent the embedded particle. The shape is arbitrary. These particles can have any shape, and the shape doesn't matter. But that happened to be a convenient shape to use. You can see the gap that's formed around it, but somewhere in that gap, a NAS has formed, and that's where the nuclear reaction actually occurs. That gap is formed. If you look on the left, you'll see a plot of the lattice parameter versus the composition. The lattice parameter increases as the composition increases. You can see it changes the volume as a result. It causes an expansion. It's 12% by the time you get to 0.6. We can apply that information to the gap theory. And on the right, I've plotted the gap dimension against the composition. I'm assuming that the active gap is 2 nanometers. I don't know what it is precisely, but that's in the ballpark, and that'll give us at least a talking point. I've plotted the consequence of 2 different sized particles. The large particle is 0.35 microns. The critical gap would form if the composition reached 0.2. So if you have a large enough sample, a large enough gap formation, you don't have to go to high composition. But on the other hand, if the particle is at 0.1 microns, you have to go up to 0.8 in composition in order to get the critical gap. Well, is there any experience in nature that would justify this particular view? Well, yes, there is. Mike McCubry had a collection, a sample of palladium all of which made excess energy. And so he could study a lot of conditions, and he studied the effect of composition. And his results are on the right. The amount of power is plotted against the D to PD ratio. So let's apply my model. Let's assume that he had in his sample a distribution of particle size, the largest of which was 0.1 micron. And that distribution is shown on the left. So when he loaded up to 0.8, according to my calculations, he should start to see heat. However, there's very few of these particles of that size there. So there'd be very few nuclear active environment formed. But as he increased the composition, smaller and smaller particles would become active because they were able to form the right size, and the amount of power would go up. If the distribution had a form, which is the Gaussian distribution shown there, if it had that basic form, then it would produce a result that had this upward curvature that you see on the right. So this particular model explains what the Kubri saw, which as far as I know, no one else has explained. So let's summarize. The rate controlling events for LENR, the number of nuclear active environment, that's pretty obvious. The number of active sites that form in this environment, that's the NAS. But now the temperature plays a role. The question is, how does the temperature impact? And I'll talk about that shortly. And then finally, the isotope distribution. If you have deuterium, you'll get a different nuclear product, and therefore a different amount of energy produced. So which isotope you use will determine the rate. Well, let's talk about the temperature. On the left, you see a plot of the log of power against 1 over T, a typical Arrhenius plot. You'll see A, B, and C noted plots. Each of those are based upon separate samples done at separate times. But they're all done in a calorimeter in using electrolytic approach and study over a similar temperature range. And they're all solid samples. Notice they all have the same slope. Now, although each of these samples has a different magnitude of power, they all have the same slope. In other words, the slope is a characteristic of the LENR process in those samples, even though you get different amounts of power occasionally. That's important to understand. Now, if you look at B was a sample that was run when the current was applied. This allowed a composition of 0.85. You can see all the points lie on a straight line. But then the current was turned off. This allowed the deuterium to leave the sample, and so the composition continuously was reduced, and it was measured periodically. Notice that all those points lie on the same line. In other words, the changing composition had no effect at all on the amount of power being produced, but yet it produced the same slope. If you look on the right, now that's a plot of temperature against the power now. And the colored points, the red and the black, are run in an electrolytic cell. And of course, there's a limited temperature. That same sample was taken out of the electrolytic cell and put into a gas loading cell. That is, it was just simply exposed to deuterium without electrolysis. And then it was run in the calorimeter. Of course, you can go to a higher temperature because you don't have any water present. Notice that the data agree. The sample behaved the same way. In other words, electrolysis there's nothing about electrolysis that makes that unique to forming LENR. You can cause the process to take place various ways having no relationship to the complexity that exists in the electrolytic process. That's also important to realize. Now, I could talk about the nature of the NAS. I'm just a little afraid that somebody would start throwing something at me because this is a very controversial aspect. If you want to talk to me privately in the presence of witnesses, I'll be happy to talk about that. But let's talk about the nature of the nuclear reaction involving the different isotopes. The big problem is explaining tritium. People have a hard time doing that. So I made that my challenge. How can I explain tritium? Well, one way of explaining it is if you introduce an electron in the process. I believe the NAS consists of a collection of electrons and nuclei which are collaborating together, but in that process, an electron could easily be sucked into the nuclear product. So that makes sense to me. But what are the consequences? If you have two deuterons coming together, and I might point out too, these equations do not describe what's happening in reality. They just simply summarize what was there before and then what we saw later. This is just simply, they don't represent reality as to what is actually happening. It's only what you start with and what you end with. So don't quarrel about the fact that there's a two-body to a one-body reaction, and you can't conserve momentum under those conditions. That's an argument we don't need to get into. Nevertheless, if you have two deuterons coming together with an electron, you get hydrogen 4. If you have a hydrogen and a deuterium coming together with an electron, you get tritium. And if you have two protons coming together, you get deuterium. So we have a nice, what would I call it, pattern. I mean, nature likes consistent patterns. And here's a nice consistent pattern. Furthermore, we can explain the neutrons that come off when people see tritium. Neutrons are produced at a very low level, and they are correlated with the amount of tritium that's being produced. And that is shown in the graph on the right. The hot fusion produces at 0, when you plot the log of tritium over neutrons. But you can see there's a collection of data, all having values that seem to center around 10 to the 6th when you look at the log of neutron ratio. What causes those neutrons to be correlated with tritium? Well, if you apply my model to that would be tritium fusing with an electron and with a deuteron to form helium or hydrogen 5, which would give off a neutron immediately. So the ratio that's produced there, which has a wide range of values, would be sensitive to the tritium to deuterium ratio in a particular sample. So I can explain that. But then I hear somebody from the back yell, "You idiot, hydrogen 4 can't form. It's known to form by giving off a neutron almost instantaneously. So all of this is nonsense." That's true. I admit to that. However, we're not working at high energy. We're working in a very low energy environment and under rather unusual conditions within the nuclear process. So I would submit that we have the opportunity to believe that it does not have to give off a neutron. But is there any evidence to support that? In 2002, or 1992, Karabat was studying the production of photons within a gas discharge. He saw lots of them, did a very good job. But along with that study, he put some CR39 in, and he got the spectrum, ionized spectrum that is shown there. Now, there's several characteristics of that spectrum that you need to focus on. First of all, it all occurs at relatively low energies, below 6 MeV. The intensity drops off in a nonlinear manner as you go to higher energies. And it consists of a number of separate energy peaks, all pretty much equally spaced. I mean, it's crude because it was CR39, but anyway, that's the basic picture you need to keep in your mind. Later, Brian Scanlon and I did a study under the identical conditions, gas discharge, and we saw the same spectrum, but because I was using a silicon barrier detector, I could determine its energy very precisely. And this is an example of the spectrum. Now, if we take from that spectrum and plot the log of the intensity against the energy, you get a straight line. In other words, you get this nonlinear decrease as you go to higher energies. Also, if you look on the right, if you plot the position in the spectrum against the energy, you get a straight line. This means that all of these peaks are equally spaced, exactly what Karabat saw. But I could do one thing more that he could not do. I could insert absorbers into this beam and note how much energy was reduced by this insertion. And by comparing that information to the NIST tables, I could show very clearly that this is not helium. Everybody assumes that helium is being given off because that's a product you see. That's what you detect. This is not helium. This is consistent, its behavior is consistent with an isotope of hydrogen. Now, which isotope of hydrogen, I don't know. But I'm encouraged to believe that it's hydrogen-4. Well, there are several implications of this idea, of this model. In the past, when people assumed that helium was being made, we have a problem because helium does not diffuse very readily within a material. So in order to get the helium out of the palladium deuteride, where it's measured in the gas, it has to be made very close to the surface. Otherwise, it could not escape. And it always bothered me why this should be true. I mean, the true surface is different than the interior, but once you go in a few microns, it's identical to the rest of the sample. So why should the reaction be favored just in that region? It just didn't make any sense. If you accept the idea of hydrogen-4, you can see that problem goes away because the hydrogen-4 diffuses very readily through palladium. And so it could escape very easily before it decayed to helium. So that problem goes away. The second problem is, if you're making helium, why doesn't the helium fragment like it does when it's produced by hot fusion? That would resolve the problem of the energy states within the helium, which obviously the energy has to be dissipated somehow or another. It also allows you to conserve momentum, because right now we really don't have a convenient way of doing that. Well, if it's hydrogen-4, that problem goes away. The helium is made as a consequence of beta emission. Edmund studied the production of radiation coming off of what looked like a cold fusion reaction. And he found that the radiation had a half-life. It had a decay, and he could measure that decay. I suggest that what he was actually measuring was the decay of hydrogen-4. Now, there are several other implications. One is, if you use pure deuterium, you will not make tritium. And that's very good to know, especially in a large-scale generator. You don't want to make tritium. So you want to use pure deuterium. If you use pure hydrogen, on the other hand, which many people are studying and which does make excess energy, you will make tritium. And the reason is that the hydrogen makes deuterium, and then that deuterium finds a proton, which makes tritium, based upon my mechanism. So you should see the slow growth of tritium in the cells that are based upon light hydrogen. Now, this would be a real disaster in a power plant that's making megawatts of power, because the amount of tritium would grow to actually dangerous levels under those conditions. And so that's another variable that needs to be considered when you apply this. Well, for success, we need three things. We need to make more of the nuclear active environment, and I've described how that could be done, and there's lots of different variations of that. Some work better than others. I happen to like mine because it seems to work quite nicely. We need to stimulate the formation of the NAS. I believe you can do that. In fact, Robert Gaddis, I believe, is doing that by applying his pulse current. That's the variable that his pulse current is affecting. And then the use of higher temperatures. Now, higher temperatures that are important. Most of my samples at 20 degrees centigrade, where most people work, look dead. It's only when I heat them that I start seeing it. And of course, as we saw earlier, the temperature has a very characteristic effect. I would suggest that many of the failures that people have reported would have been successes if they had simply worked at a higher temperature. Okay, thank you for your attention. I'm willing to duck anything you throw.
Hi, it's Ruby. Did I miss you saying that you were going to tell us how you made this material?
Yes.
Did you say that?
Well, yes, you incorporate particles of the correct size into palladium. Now, I do that because I'm self-funded. I do that in the most simple way possible. I take a piece of palladium, roll it out, paint on the surface using acetone as make a slurry, the suitable particles, roll this up so that now this surface is incorporated into the structure, melt it with a flame. I get a little button, roll that out into a convenient shape and size, heat it in a furnace and air to oxidize the surface to make it active, put it in deuterium gas, load it up, reacts very rapidly with deuterium, and then put it in the calorimeter, and it makes heat instantly. Now, the only challenge, of course, is getting the right size particle. If you use the wrong size particle, nothing will happen. And right now, I'm exploring with more precision the right size particle. Anyway, that's the way you do it. Now, if you're going to apply this industrially, I think the use of a material, even this material, is a waste of time. Materials are too difficult to create in a reproducible way. You have to do it, make the material by nanomachining. And I would suggest that if it's cracks, gaps, we identify the gap width, and then machine those by nanomachining techniques, which are available now into nickel, for example, and make the concentration sufficient that it produces a large amount of power, but not enough to melt the sample. And then you could turn this out in tons of amount in a totally reproducible way. I think that's the only way this is going to be made practical. And I would suggest that the sooner you get to work looking at it from that point of view, the quicker we'll actually have something that works.
Another question. Basically, you just answered it, but I mean, why not use a focused ion beam milling machine, which is commercially available from FEI, for example, and other places, for drilling or boring holes in semiconductors? It's a standard tool, and drill or bore a bunch of nano-sized holes on the surface of, say, palladium, finely, controlled, smooth, polished palladium, and then see if your theory is correct. Put some deuterium in the holes, make them various depths, various diameters, various angles if you like. You can cover them up again and make them voids if you want, and see if in fact you know exactly where the holes are because you drilled them there. Does it work? Do you go back and see evidence of reactions after you've waited a certain period or done whatever it is, whatever magic sauce you need to make, your reactions happen, and study it that way? And those are existing tools. They're, I can give you the address of FEI, and they'd probably volunteer to be partners, maybe. I don't know. I mean, maybe we could be talked into it.
Well, I didn't detect a question there, but let me expand on that. It doesn't matter. I don't think the shape of the crack or the material, the gap, is important. I mean, from the point of view of the atom, all shapes are the same. So, but you do have it to make it the right size. So with nanomachining, you have total control. I mean, it's relatively easy to nanomachine a gap at 10 nanometers. That's too big, and there's obvious ways of making it smaller. And the challenge would be to apply those slowly until you reached the critical size, and all of a sudden it would turn on, and then that's the size that you need to make on a regular basis. But any technique that would produce the right size hole would work.
In the semiconductor industry, it's all, the FEI machines are programmable. You can make them do anything you want, any size hole you want, down to some atomic limit. I don't know what the exact limit is. It may depend on the material. But calling FEI and just, getting them on board, I mean, would just take a phone call, or more than a phone call, but it seems like an obvious thing to do. I mean, it's a standard technology. It's sitting there waiting to be used. And it's been there for years. It's not new. I mean, we could probably, find some people that might be interested in doing that right here today, if we were to call on the phone.
Yes, and I'm talking to people that do have that. The problem is it costs money.
Yeah, but I mean, the world's at stake here.
Yeah.
We're going to want to help.
Anyway, let's talk about that during the intermission, and I'd love to explore your ideas.
We have time for one more question.
Good morning. Thanks for your talk, Ed. What's the size ballpark that you think we should look in for the NAs? 10 nanometers you just mentioned and below? Is that a reasonable starting size for the manufactured holes, defects, whatever you want to call them?
Well, I think 1 nanometer is too small and 10 nanometers is too large.
Okay.
So I picked 2 nanometers as just a talking point. We obviously would have to explore that in much more detail to know what exactly to focus on. But the big issue is that we need to focus on a size of gap. That hasn't been considered in the past.
One could imagine a parametric study starting at the lower end of nanomachining and just making smaller and smaller sizes and samples and testing them all. So is that something you would recommend?
Yeah, well, let's talk about this because there's a huge amount that I have not said that needs to be said if you're really serious about going down that road.